Picture this, a river of invisible energy flowing endlessly from the heart of our sun, racing across the vast emptiness of space at unimaginable speeds. This is the solar wind, a silent, invisible force that has shaped the very fabric of our solar system for billions of years. It's not just a stream of charged particles, it's a cosmic storyteller, carrying secrets about the sun's fiery heart and its influence on every planet, moon, and comet in its path. Tonight, as you drift into the stars, we'll unravel the mystery of this powerful force, exploring how it dances with Earth's magnetic field, paints the skies with auroras, and even shapes the destiny of distant worlds. So, wherever you are, and whatever time it is, let's embark on this journey together as we uncover the hidden wonders of the solar wind, a force as ancient as the sun itself and as mysterious as the universe it travels through. Now, let's journey to the very source of this cosmic river, the sun itself. The solar wind begins its life in the sun's corona, the outermost layer of its atmosphere. Unlike the sun's visible surface, which glows with a steady light, the corona is a realm of extreme heat and energy, reaching temperatures of millions of degrees. It's here, in this searing outer layer, that the solar wind is born. The process starts with the sun's magnetic field, which twists and turns in a chaotic dance, creating loops and arches of energy. These magnetic fields trap charged particles, heating them to incredible temperatures, but the corona's gravity isn't strong enough to hold onto these superheated particles forever. Eventually, they break free, streaming outward into space at speeds that can reach hundreds of kilometers per second. This escape isn't random, it's driven by the sun's immense energy. As the particles accelerate, they form the solar wind, a continuous flow of protons, electrons, and other charged particles. It's like a cosmic exhale, a breath of energy that carries the sun's influence far beyond its fiery surface. But what propels these particles so far and so fast? The answer lies in the sun's magnetic activity and the pressure of its intense heat. Together, they create a force powerful enough to push the solar wind across the vast emptiness of space, shaping the environment of our entire solar system. As we continue our journey, we'll see how this stream of charged particles travels through the cosmos, interacting with planets, moons, and even the distant edges of our solar system. But for now, let's marvel at the birthplace of the solar wind, a place where the sun's fiery heart sends its energy out into the universe, one particle at a time. Now that we've explored where the solar wind begins, let's take a closer look at what it's actually made of. The solar wind isn't just a uniform stream of energy. It's a complex mixture of charged particles, each with its own role in shaping the cosmos. At its core, the solar wind is composed of three main types of particles: protons, electrons, and alpha particles. Protons, which are positively charged particles, make up the majority of the solar wind. These tiny particles are the building blocks of hydrogen atoms, and their abundance reflects the sun's composition, which is primarily hydrogen. Electrons, on the other hand, are negatively charged particles that balance out the positive charge of the protons. Together, protons and electrons create a flow of energy that carries the sun's influence across the solar system. But there's another key player in this cosmic mix: alpha particles. These are essentially helium nuclei, made up of 2 protons and 2 neutrons. While they're less abundant than protons and electrons, alpha particles are heavier and carry more energy, making them an important part of the solar wind's impact on space. Why does this matter? Each type of particle contributes to the solar wind's behavior and its interactions with the planets and other celestial bodies. Protons and electrons, for example, are lightweight and fast, allowing them to travel great distances. Alpha particles, with their greater mass, add a punch of energy that can influence magnetic fields and even shape the atmospheres of planets. Together, these particles create a dynamic and ever-changing flow of energy that extends far beyond the sun. They carry not just the sun's heat and light, but also its magnetic influence, shaping the environment of our solar system in ways we're still working to understand. As we move forward, we'll see how this intricate mix of particles interacts with the worlds around us, from Earth's protective magnetosphere to the distant reaches of interstellar space. But for now, let's appreciate the solar wind for what it is: a cosmic cocktail of charged particles, each playing a vital role in the story of our solar system. Now that we've explored the composition of the solar wind, let's shift our focus to another fascinating aspect: its speed. The solar wind doesn't travel at a constant pace. It comes in both slow and fast streams, each with its own unique characteristics and origins. Slow solar wind typically moves at speeds of around 300 to 400 kilometers per second. This slower stream often originates from regions near the sun's equator, where the magnetic field is more closed and stable. These areas allow particles to escape more gradually, creating a steady but slower flow. On the other hand, fast solar wind can reach speeds of up to 700 to 800 kilometers per second. This faster stream usually comes from coronal holes, areas in the sun's corona, where the magnetic field lines are open, allowing particles to escape more freely and at higher speeds. Coronal holes are often found near the sun's poles, and their presence can significantly influence the speed and intensity of the solar wind. But what causes these differences in speed? It all comes down to the sun's magnetic field and the conditions in its corona. In regions with closed magnetic loops, particles are trapped and released more slowly, resulting in the slower solar wind. In contrast, open magnetic fields and coronal holes act like highways, accelerating particles outward at much higher speeds. These varying speeds have a profound impact on the solar system. Fast solar wind can catch up to slower streams, creating shock waves and disturbances in space. These interactions can lead to space weather events, such as geomagnetic storms, which can affect satellites, communication systems, and even power grids on Earth. Understanding the speed of the solar wind isn't just about measuring numbers, it's about uncovering how the sun's dynamic behavior shapes the environment around us. From the slow, steady streams to the fast, energetic bursts, each type of solar wind plays a role in the cosmic dance that defines our solar system. As we continue our journey, we'll see how these varying speeds influence the solar wind's interactions with planets, moons, and even the boundaries of interstellar space. But for now, let's marvel at the incredible diversity of the solar wind, a force that moves not just with power, but with purpose. Now that we've marveled at the varying speeds of the solar wind, let's follow its journey as it travels through the vast expanse of our solar system. Picture the solar wind as a cosmic river, flowing outward from the sun and carrying with it a stream of charged particles. This river doesn't just drift aimlessly, it interacts with everything in its path, shaping the environment of planets, moons, and other celestial bodies. As the solar wind leaves the sun, it begins its voyage through the inner solar system. The first stop on this journey is Mercury, the closest planet to the sun. Here, the solar wind encounters a weak magnetic field and a thin atmosphere, allowing it to directly impact the planet's surface. Over time, this interaction has contributed to the creation of Mercury's unique, cratered landscape, as the solar wind erodes and alters its surface materials. Moving outward, the solar wind reaches Venus. Unlike Mercury, Venus has a dense atmosphere, but it lacks a strong magnetic field. This means the solar wind interacts with the planet's upper atmosphere, gradually stripping away particles and contributing to the loss of its water over billions of years. This process highlights how the solar wind can shape the evolution of a planet's atmosphere, even without a magnetic shield. Next, the solar wind arrives at Earth, where it meets our planet's robust magnetic field. This interaction creates the magnetosphere, a protective bubble that deflects most of the solar wind's charged particles. However, some particles manage to slip through, especially during intense solar storms, leading to the breathtaking auroras that light up our polar skies. These displays are a vivid reminder of the solar wind's power and its ability to influence our planet in stunning ways. Beyond Earth, the solar wind continues its journey to Mars. The red planet, with its thin atmosphere and weak magnetic field, is particularly vulnerable to the solar wind's effects. Over time, this interaction has played a significant role in stripping away much of Mars' atmosphere, leaving behind the barren, desert-like world we see today. As the solar wind travels further into the outer solar system, it encounters the gas giants Jupiter, Saturn, Uranus, and Neptune. These planets have strong magnetic fields, which interact with the solar wind to create massive magnetospheres and spectacular auroras. Jupiter, for example, boasts some of the most intense auroras in the solar system, a direct result of its powerful magnetic field colliding with the solar wind. Even beyond the planets, the solar wind continues to influence the solar system. It shapes the tails of comets, pushing particles away from the sun and creating the iconic glowing tails we see in the night sky. It also interacts with the icy bodies of the Kuiper belt, the distant region beyond Neptune that's home to dwarf planets like Pluto. The solar wind's journey doesn't end there. It travels all the way to the edge of the solar system, where it eventually slows down and merges with the interstellar medium. This boundary, known as the Heliosphere, marks the limit of the sun's influence and the beginning of interstellar space. As we trace the solar wind's path, it becomes clear that this stream of charged particles is more than just a cosmic breeze. It's a dynamic force that shapes the very fabric of our solar system. From the scorching surface of Mercury to the icy reaches of the Kuiper belt, the solar wind leaves its mark on everything it touches. In our next exploration, we'll dive deeper into how the solar wind interacts with Earth's magnetosphere, creating phenomena like the auroras and influencing our planet's space environment. But for now, let's appreciate the solar wind's incredible journey, a testament to the sun's far-reaching influence across the cosmos. Now, let's take a closer look at how the solar wind interacts with Earth's magnetic field, a relationship that not only protects our planet, but also creates some of the most mesmerizing displays in the night sky. As the solar wind approaches Earth, it doesn't just crash into our atmosphere. Instead, it encounters Earth's magnetic field, a powerful shield generated by the movement of molten iron in our planet's core. This magnetic field extends far into space, forming a protective bubble known as the magnetosphere. The magnetosphere acts like a cosmic force field, deflecting the majority of the solar wind's charged particles away from Earth. Without this shield, the solar wind would strip away our atmosphere over time, much like it has done on Mars. But the interaction between the solar wind and the magnetosphere is far from simple. When the solar wind hits the magnetosphere, it compresses the side facing the sun, while stretching the opposite side into a long tail, much like a comet's tail. During periods of intense solar activity, such as solar storms or coronal mass ejections, the solar wind becomes stronger and more turbulent. These events can cause the magnetosphere to become overloaded, allowing some charged particles to slip through. When this happens, the particles are funneled along Earth's magnetic field lines toward the poles. As they collide with gases in the upper atmosphere, they release energy in the form of light, creating the stunning auroras we know as the northern and southern lights. These auroras are more than just beautiful light shows. They're a direct result of the solar wind's interaction with our planet's magnetic field. The colors we see depend on the type of gas particles involved. Oxygen produces green and red hues, while nitrogen creates blue and purple tones. The intensity of the auroras can vary, from faint glows to vibrant curtains of light dancing across the sky, depending on the strength of the solar wind and the conditions in Earth's magnetosphere. But the magnetosphere's role goes beyond creating auroras. It also protects satellites, spacecraft, and even astronauts from the harmful effects of the solar wind. Without this shield, the charged particles could damage electronics, disrupt communication systems, and pose serious risks to human health. In fact, understanding the magnetosphere is crucial for planning future space missions, especially those that venture beyond Earth's protective bubble. As we continue to study the solar wind and its interaction with Earth's magnetosphere, we gain valuable insights into how our planet fits into the larger cosmic environment. This dynamic relationship not only shapes the space around us, but also reminds us of the delicate balance that makes life on Earth possible. Next, we'll explore how the solar wind influences space weather, from solar storms to their impact on modern technology. But for now, let's marvel at the incredible interplay between the solar wind and Earth's magnetic field, a partnership that keeps our planet safe while painting the skies with light. Now, let's turn our attention to the solar wind's role in shaping space weather, a phenomenon that affects not just our planet, but the entire solar system. Space weather refers to the conditions in space influenced by the sun's activity, and the solar wind is one of its primary drivers. This constant stream of charged particles doesn't just flow peacefully through space, it carries with it the potential for dramatic and sometimes disruptive events. When the sun experiences periods of heightened activity, such as solar flares or coronal mass ejections, the solar wind becomes more intense. These events send bursts of energy and charged particles racing through space at incredible speeds. When these bursts reach Earth, they interact with our magnetosphere, often triggering geomagnetic storms. These storms can have a wide range of effects, from the awe-inspiring auroras we've already discussed to more serious consequences for modern technology. One of the most significant impacts of space weather is on satellites orbiting Earth. The charged particles in the solar wind can interfere with satellite electronics, causing malfunctions or even permanent damage. This is particularly concerning for communication satellites, which play a vital role in global connectivity. Disruptions to these systems can affect everything from television broadcasts to GPS navigation, highlighting just how interconnected our modern world is with the space environment. But it's not just satellites that are at risk. The solar wind's influence on space weather can also affect power grids on Earth. During intense geomagnetic storms, the influx of charged particles can induce electric currents in power lines, potentially leading to blackouts or damage to electrical infrastructure. In fact, one of the most famous examples of this occurred in 1989, when a powerful solar storm caused a widespread blackout in Quebec, Canada, leaving millions without power for hours. For astronauts and spacecraft, the solar wind poses additional challenges. Beyond Earth's protective magnetosphere, the charged particles can pose serious health risks, increasing the likelihood of radiation exposure. This is a critical consideration for future missions to the Moon, Mars, and beyond, where shielding from the solar wind will be essential for the safety of crew members and the success of the mission. Understanding and predicting space weather is therefore crucial for protecting both our technology and our exploration efforts. Scientists use a combination of ground-based observatories and space-based instruments to monitor the sun's activity and track the solar wind's behavior. By studying these patterns, they can provide early warnings of potential geomagnetic storms, giving us time to prepare and mitigate their effects. As we continue to explore the mysteries of the solar wind and its influence on space weather, we gain not only a deeper understanding of our cosmic environment, but also the tools to safeguard our increasingly technology-dependent world. Next, we'll venture further into the solar system to explore the Heliosphere, the vast bubble created by the solar wind that defines the boundaries of our cosmic neighborhood. But for now, let's reflect on the solar wind's dual nature, both a source of beauty and a force to be reckoned with in the ever-changing landscape of space weather. Now, let's journey beyond Earth and into the vast expanse of the solar system to explore the Heliosphere, a colossal bubble shaped by the solar wind. Imagine the Heliosphere as a protective shield, extending far beyond the orbits of the planets, created by the constant flow of charged particles streaming from the sun. This immense structure is not just a boundary, it's a dynamic region where the solar wind interacts with the interstellar medium, the sparse matter and radiation that fills the space between stars. The heliosphere acts as a buffer, shielding our solar system from the majority of cosmic rays and other high-energy particles that travel through interstellar space. Without this protective bubble, these particles could bombard the planets, potentially altering their atmospheres and making space travel far more hazardous. The shape of the heliosphere isn't uniform. It's more like a teardrop, elongated in the direction opposite to the sun's motion through the galaxy. This asymmetry is caused by the pressure of the interstellar medium pressing against the solar wind as the sun moves through space. At the very edge of the heliosphere lies the heliopause, the boundary where the solar wind's influence wanes and interstellar space begins. This region is where the solar wind slows down and merges with the interstellar medium, marking the outermost limit of the sun's reach. Beyond this point, the environment is dominated by the particles and magnetic fields of the wider galaxy. Understanding the heliosphere is crucial for grasping how our solar system interacts with the broader universe. It's not just a static boundary, it's a dynamic, ever-changing region that responds to fluctuations in the solar wind and the pressure of the interstellar medium. By studying the heliosphere, scientists gain insights into the sun's influence on its surroundings and the nature of the space beyond our cosmic neighborhood. As we continue to explore the mysteries of the heliosphere, we'll next delve into the termination shock, the point where the solar wind begins to slow down as it collides with the interstellar medium. This fascinating boundary marks the beginning of the heliosphere's outer reaches and offers a glimpse into the complex interplay between the sun and the galaxy beyond. But for now, let's marvel at the Heliosphere, a testament to the sun's enduring influence and the intricate balance that defines our place in the cosmos. Now, let's venture deeper into the outer reaches of the Heliosphere, where the solar wind meets its first major obstacle, the termination shock. This boundary marks the point where the solar wind, which has been racing outward from the sun at incredible speeds, begins to slow down dramatically as it collides with the interstellar medium. Think of it as a cosmic speed bump, where the fast-moving particles from the sun are forced to decelerate, creating a turbulent and fascinating region of space. The termination shock isn't a sharp, well-defined line, but rather a broad, dynamic zone where the solar wind's energy is redistributed. As the charged particles from the sun slam into the denser interstellar medium, they compress and heat up, forming a kind of shock wave. This process is similar to how water waves slow down and spread out when they hit a shoreline. The exact location of the termination shock varies depending on the strength of the solar wind and the pressure of the interstellar medium, but it's estimated to lie roughly between 80 and 100 astronomical units from the sun. That's about 80 to 100 times the distance between Earth and the sun. What makes the termination shock so intriguing is that it's not just a boundary, it's a place of transformation. Here, the solar wind transitions from supersonic speeds to subsonic, meaning it slows down to below the speed of sound in space. This change creates a chaotic environment filled with energetic particles and magnetic fields, offering scientists a unique laboratory to study how the sun's influence wanes as it interacts with the broader galaxy. The Voyager 1 spacecraft, humanity's farthest reaching probe, crossed the termination shock in 2004, providing the first direct measurements of this mysterious region. Its observations revealed that the shock isn't uniform but fluctuates over time, responding to changes in the sun's activity and the pressure of the interstellar medium. These findings have deepened our understanding of how the solar wind shapes the heliosphere and how our solar system interacts with the galaxy beyond. As we move beyond the termination shock, we approach the heliopause, the true edge of the sun's influence. But for now, the termination shock stands as a testament to the sun's power and the complex interplay between our star and the vast expanse of interstellar space. It's a reminder that even in the farthest reaches of the solar system, the sun's presence is still felt, shaping the environment in ways we're only beginning to understand. Now, as we journey even farther into the depths of space, we arrive at the heliopause, the final frontier, where the solar wind meets its ultimate limit. This boundary marks the edge of the sun's influence, where the outward push of the solar wind is balanced by the inward pressure of interstellar space. Imagine it as the cosmic shoreline where the sun's reach ends and the vast ocean of the galaxy begins. The heliopause is not a solid wall, but a dynamic, ever-shifting boundary. Here, the solar wind, which has traveled billions of miles from the sun, finally loses its momentum and merges with the interstellar medium, the sparse gas and dust that fill the space between stars. This collision creates a turbulent zone where the sun's magnetic field weakens and the flow of charged particles slows to a near halt. It's a place of transition, where the familiar environment of our solar system gives way to the uncharted territory of interstellar space. One of the most fascinating aspects of the heliopause is its role in defining the limits of our solar system. Beyond this boundary, the sun's magnetic field and the flow of solar wind no longer dominate. Instead, the environment is shaped by the magnetic fields and particles of the galaxy itself. This makes the heliopause a critical point for understanding how our solar system interacts with the broader Milky Way. The Voyager 1 spacecraft made history in 2012 when it became the first human-made object to cross the heliopause, providing us with unprecedented data about this mysterious region. Its measurements revealed that the heliopause is not a smooth, uniform boundary, but a complex, fluctuating interface. The pressure from the interstellar medium can push the heliopause inward, while bursts of solar activity can temporarily expand it outward, creating a dynamic and ever-changing edge. Crossing the heliopause also revealed something unexpected. The density of particles in interstellar space is higher than scientists had predicted. This discovery has led to new questions about the nature of the interstellar medium and how it interacts with the solar wind. It's a reminder that even at the edge of our solar system, there are still mysteries waiting to be unraveled. The heliopause is more than just a boundary, it's a gateway. It represents the point where the sun's influence fades and the influence of the galaxy takes over. For scientists, It's a crucial area of study, offering insights into how stars shape their surroundings and how our solar system fits into the larger cosmic picture. As we continue to explore this distant frontier, we gain a deeper understanding of not just our place in the universe, but the forces that connect us to the stars beyond. Now, let's turn our attention to one of the most visually stunning effects of the solar wind, its impact on comets. These icy wanderers of the solar system are transformed into celestial spectacles as they journey closer to the sun, and the solar wind plays a starring role in this dramatic transformation. When a comet approaches the sun, the heat causes its icy surface to vaporize, releasing gas and dust into space. This material forms a glowing cloud around the comet, known as the coma. But it's the solar wind that takes this process a step further, shaping the coma into the comet's iconic tails. The solar wind, with its stream of charged particles, pushes against the gas and dust in the coma, creating two distinct tails. The first is the ion tail, made up of charged particles that are directly influenced by the solar wind's magnetic field. This tail always points directly away from the sun, no matter which direction the comet is moving. It's often blue in color and can stretch for millions of miles, a shimmering trail of light that dances in the solar wind's flow. The second tail, the dust tail, is made of larger particles that are less affected by the solar wind's magnetic field. Instead, sunlight exerts a gentle pressure on these particles, pushing them into a curved tail that follows the comet's path. This tail is usually broader and more diffuse, glowing with a yellowish hue as it reflects sunlight. Together, these tails create the breathtaking sight that has captivated humans for centuries. But the solar wind doesn't just shape comets visually, it also influences their behavior. As comets travel through the solar system, the solar wind can erode their surfaces, stripping away material and altering their composition over time. This process can even cause comets to break apart if they pass too close to the sun, leaving behind trails of debris that can become meteor showers when Earth crosses their path. The interaction between comets and the solar wind also provides valuable insights for scientists. By studying the composition of comet tails, researchers can learn more about the solar wind's properties and how it interacts with different materials in space. Comets act like cosmic probes, revealing the invisible forces at work in our solar system. In many ways, comets are a testament to the solar wind's power. They remind us that even the smallest particles, carried on the sun's breath, can shape the cosmos in profound and beautiful ways. As we continue to explore the mysteries of the solar wind, comets serve as both a canvas and a clue, helping us unravel the secrets of our dynamic solar system. Next, we'll explore how the solar wind interacts with the atmospheres of planets, shaping their environments in ways that are just as fascinating and sometimes just as dramatic. Now, let's shift our focus to another fascinating aspect of the solar wind, its ability to shape the very atmospheres of planets. While comets dazzle us with their glowing tails, the solar wind's influence on planetary atmospheres reveals a more subtle, yet equally profound, interaction. Planets with strong magnetic fields, like Earth, are well protected from the solar wind's relentless stream of charged particles. Our planet's magnetic field acts like a shield, deflecting the solar wind and preventing it from stripping away our atmosphere. But not all planets are so fortunate. Those without strong magnetic fields are far more vulnerable to the solar wind's erosive power. Take Mars, for example. Billions of years ago, Mars likely had a thicker atmosphere, possibly even supporting liquid water on its surface. But over time, the solar wind has played a significant role in thinning its atmosphere. Without a global magnetic field to protect it, Mars' atmosphere has been slowly eroded, leaving behind the thin, cold air we see today. Scientists believe this process has been ongoing for millions, if not billions, of years, transforming Mars from a potentially habitable world into the barren desert we know now. Venus, on the other hand, presents a different story. Despite lacking a strong magnetic field, Venus has managed to retain a dense atmosphere. This is partly due to its thick atmosphere, which creates a kind of natural barrier against the solar wind. However, even Venus isn't entirely immune. The solar wind interacts with Venus' upper atmosphere, stripping away lighter gases like hydrogen and helium over time. This process, known as atmospheric escape, has shaped Venus into the hot, inhospitable world it is today. Even Mercury, the closest planet to the Sun, feels the solar wind's effects. With only a weak magnetic field, Mercury's thin atmosphere, or exosphere, is constantly bombarded by the solar wind. This bombardment not only strips away particles, but also contributes to the planet's unique surface chemistry, as the solar wind implants charged particles directly into Mercury's soil. The solar wind's ability to strip away atmospheres isn't just a destructive force, it's also a key factor in understanding how planets evolve over time. By studying how the solar wind interacts with different planetary atmospheres, scientists can piece together the history of our solar system and even predict the future of other worlds. As we continue to explore the mysteries of the solar wind, its impact on planetary atmospheres reminds us of the delicate balance that shapes the environments of planets. Whether it's the slow erosion of Mars' atmosphere or the complex interactions on Venus and Mercury, the solar wind is a powerful force that continues to shape the story of our solar system. Next, we'll take a closer look at how the solar wind affects the Moon, our closest celestial neighbor, and the surprising ways it has left its mark on the lunar surface. Turning our gaze to the Moon, we find yet another fascinating chapter in the solar wind story. Unlike Earth, the Moon lacks both an atmosphere and a global magnetic field, leaving its surface completely exposed to the relentless flow of charged particles from the Sun. This direct interaction has left a lasting imprint on the lunar landscape, shaping its surface in ways that continue to intrigue scientists. One of the most significant effects of the solar wind on the Moon is the creation of what we call lunar soil, or regolith. Over billions of years, the constant bombardment of charged particles has broken down the Moon's surface rocks into fine, powdery particles. This process, known as space weathering, is driven by the solar wind's ability to erode and alter the chemical composition of the Moon's surface. The result is a layer of regolith that covers much of the Moon, giving it that distinctive, dusty appearance we see from Earth. But the solar wind's influence doesn't stop there. As these charged particles strike the moon's surface, they become embedded in the regolith, creating a kind of solar wind archive. Scientists have discovered that the moon's soil contains traces of hydrogen, helium, and other elements that were carried by the solar wind. These implanted particles provide valuable clues about the sun's history and the behavior of the solar wind over time. In fact, studying these elements has helped researchers better understand the sun's activity and its impact on the solar system. Another intriguing effect of the solar wind on the moon is the creation of a faint, temporary atmosphere. While the moon doesn't have a permanent atmosphere, the solar wind can ionize atoms on its surface, releasing them into a thin, transient layer of gas. This process, known as sputtering, occurs when the solar wind knocks atoms loose from the lunar surface, creating a temporary exosphere. Though this exosphere is incredibly thin compared to Earth's atmosphere, it's a reminder of the dynamic interactions between the solar wind and the moon. The moon's exposure to the solar wind also has implications for future lunar exploration. The charged particles embedded in the regolith could pose challenges for astronauts, as they may affect equipment and even human health. At the same time, these particles could also be a valuable resource. For example, the hydrogen and helium trapped in the lunar soil could potentially be harvested to support future missions, providing fuel or other essential materials. As we continue to study the moon, the solar wind's effects on its surface remind us of the intricate connections between the sun and the bodies in our solar system. From the creation of lunar soil to the implantation of charged particles, the solar wind has left its mark on the moon in ways that continue to shape our understanding of both the moon and the sun. Next, we'll explore how the solar wind interacts with Mars, a planet that has undergone dramatic changes due to its exposure to this powerful stream of charged particles. Now, let's turn our attention to Mars, a planet that tells a story of dramatic transformation under the influence of the solar wind. Unlike Earth, Mars lacks a strong global magnetic field, leaving its atmosphere vulnerable to the relentless stream of charged particles from the sun. Over billions of years, this exposure has played a key role in the thinning of Mars' atmosphere, shaping the planet into the cold, barren world we see today. The solar wind's impact on Mars begins with its ability to strip away atmospheric particles. Without a robust magnetic field to deflect the charged particles, the solar wind interacts directly with Mars' upper atmosphere. This process, known as atmospheric sputtering, occurs when the solar wind's energy knocks atoms and molecules loose from the atmosphere, sending them spiraling into space. Over time, this has led to a significant loss of gases like carbon dioxide and water vapor, which were once abundant on Mars. Scientists believe that Mars may have once had a thicker atmosphere, capable of supporting liquid water and potentially even life. However, as the solar wind gradually eroded its atmosphere, the planet's climate changed dramatically. The loss of atmospheric pressure and greenhouse gases caused temperatures to drop, leading to the freezing and evaporation of surface water. Today, Mars' atmosphere is less than 1% as dense as Earth's, a stark reminder of the solar wind's power to reshape a planet. One of the most compelling pieces of evidence for this process comes from NASA's MAVEN mission, which has been studying Mars' upper atmosphere since 2014. MAVEN observations have shown that the rate of atmospheric loss increases during solar storms, when the sun releases bursts of charged particles at higher speeds. These events accelerate the erosion of Mars' atmosphere, providing a glimpse into how the solar wind has shaped the planet over billions of years. But the story doesn't end there. The solar wind's effects on Mars also have implications for future exploration. The thin atmosphere poses challenges for landing spacecraft and protecting astronauts from radiation. At the same time, understanding how the solar wind has altered Mars' atmosphere could help scientists develop strategies to mitigate its effects, potentially paving the way for human missions to the Red Planet. As we explore Mars, the solar wind's role in its atmospheric loss serves as a powerful reminder of the dynamic forces at work in our solar system. From its once thick atmosphere to its current barren state, Mars stands as a testament to the solar wind's ability to transform worlds over time. Next, we'll journey to Venus, a planet with a dense atmosphere but no magnetic field, to uncover how the solar wind interacts with this enigmatic world. Now, let's shift our gaze to Venus, a world that presents a fascinating contrast to Mars. While Venus also lacks a global magnetic field, its dense atmosphere creates a unique interaction with the solar wind, offering a different perspective on how charged particles from the sun can shape a planet. Venus' atmosphere is incredibly thick, composed mostly of carbon dioxide with clouds of sulfuric acid. This dense blanket of gas creates a surface pressure more than 90 times that of Earth's, making it one of the most hostile environments in the solar system. Despite this, Venus has no magnetic field to shield it from the solar wind. Instead, its atmosphere itself acts as a buffer, absorbing and deflecting the charged particles in a way that sets it apart from other planets. When the solar wind reaches Venus, it doesn't strip away the atmosphere as dramatically as it does on Mars. Instead, the dense atmosphere interacts with the solar wind in a process called ion pickup. Here, the solar wind's energy ionizes particles in Venus' upper atmosphere, creating a layer of charged particles. These ions are then carried away by the solar wind, but the sheer density of Venus' atmosphere means this process happens at a much slower rate compared to Mars. One of the most intriguing aspects of this interaction is the formation of an induced magnetosphere. Unlike Earth's natural magnetosphere, which is generated by its magnetic field, Venus' magnetosphere is created by the interaction between the solar wind and its ionosphere, the upper layer of its atmosphere. This induced magnetosphere helps deflect some of the solar wind's energy, protecting the lower atmosphere from rapid erosion. However, this doesn't mean Venus is entirely immune to the solar wind's effects. Over time, the slow but steady loss of atmospheric particles has contributed to changes in the planet's composition. Scientists believe that Venus may have once had more water in its atmosphere, but the solar wind, combined with the planet's extreme greenhouse effect, led to the evaporation and eventual escape of this water into space. The study of Venus' interaction with the solar wind has been greatly advanced by missions like the European Space Agency's Venus Express, which orbited the planet from 2006 to 2014. These observations have revealed how the solar wind shapes the upper atmosphere and influences the planet's long-term evolution. As we explore Venus, we see a world where the solar wind's impact is subtle yet significant. Its dense atmosphere and lack of a magnetic field create a delicate balance, one that has allowed Venus to retain its thick atmosphere while still being shaped by the sun's charged particles. This unique interplay offers valuable insights into how planetary atmospheres evolve under the influence of the solar wind. Next, we'll travel to Mercury, the closest planet to the Sun, to uncover how the solar wind interacts with its weak magnetic field and scorching surface. Now, let's turn our attention to Mercury, the smallest and closest planet to the Sun. Despite its proximity to our star, Mercury has a surprisingly weak magnetic field, which makes its interaction with the solar wind a fascinating subject of study. Mercury's magnetic field is only about 1% as strong as Earth's, but it still plays a crucial role in shaping how the solar wind affects the planet. Unlike Venus or Mars, Mercury's magnetic field, though weak, creates a magnetosphere, a protective bubble that deflects some of the solar wind's charged particles. However, because the magnetic field is so faint, this magnetosphere is much smaller and less effective than Earth's. When the solar wind reaches Mercury, it compresses the planet's magnetosphere on the side facing the Sun, while stretching it into a long tail on the opposite side. This creates a dynamic environment where the solar wind can directly interact with Mercury's surface, especially in regions where the magnetic field is weakest. These interactions lead to the creation of what scientists call magnetic cusps, areas where solar wind particles can funnel down to the surface, depositing energy and even contributing to the planet's thin exosphere. Mercury's exosphere, a tenuous layer of gas surrounding the planet, is constantly being replenished and stripped away by the solar wind. Elements like sodium, potassium, and calcium are knocked off the surface by the impact of solar wind particles, creating a faint but detectable atmosphere. Over time, this process has contributed to the erosion of Mercury's surface, leaving it heavily cratered and barren. One of the most striking features of Mercury's interaction with the solar wind is its ability to generate auroras, though not in the way we see on Earth. Instead of colorful displays in the sky, Mercury's auroras are created when solar wind particles interact with the planet's magnetic field, producing bursts of X-rays that can be detected by spacecraft. These X-ray auroras are a unique phenomenon, offering scientists a glimpse into the complex interplay between the solar wind and planetary magnetic fields. The study of Mercury's interaction with the solar wind has been greatly enhanced by missions like NASA's MESSENGER, which orbited the planet from 2011 to 2015. Data from MESSENGER revealed how the solar wind shapes Mercury's magnetosphere and exosphere, providing valuable insights into the processes that govern the planet's environment. As we explore Mercury, we see a world where the solar wind's influence is both direct and profound. Its weak magnetic field and close proximity to the Sun make it a unique laboratory for understanding how charged particles from our star shape the surfaces and atmospheres of rocky planets. This knowledge not only deepens our understanding of Mercury, but also helps us better comprehend the broader dynamics of our solar system. Next, we'll journey to the outer planets, where the solar wind interacts with the gas giants and their powerful magnetic fields, creating some of the most spectacular phenomena in the solar system. Now, let's venture beyond the rocky inner planets and into the realm of the gas giants, where the solar wind meets some of the most powerful magnetic fields in the solar system. These colossal planets, Jupiter, Saturn, Uranus, and Neptune, are not only massive in size, but also in their ability to shape the solar wind's journey through space. Jupiter, the largest planet in our solar system, boasts a magnetic field so strong that it dwarfs Earth's by more than 20,000 times. This immense magnetic field creates a magnetosphere that extends millions of kilometers into space, acting like a giant shield against the solar wind. When the solar wind collides with Jupiter's magnetosphere, it compresses the field on the sunward side and stretches it into an enormous tail on the opposite side. This interaction generates some of the most intense auroras ever observed, visible even from Earth with powerful telescopes. Saturn, with its iconic rings, also has a strong magnetic field, though not as powerful as Jupiter's. The solar wind's interaction with Saturn's magnetosphere produces breathtaking auroras that dance around the planet's poles. These auroras are not only beautiful, but also provide scientists with clues about the planet's internal structure and the dynamics of its magnetic field. Uranus and Neptune, the ice giants, present a different kind of interaction with the solar wind. Their magnetic fields are unique because they are tilted at extreme angles relative to their rotational axes. This unusual alignment causes the solar wind to interact with their magnetospheres in complex and unpredictable ways, leading to auroras that are irregular and harder to predict compared to those on Jupiter or Saturn. One of the most fascinating aspects of the solar wind's interaction with the outer planets is how it influences their moons. For example, Jupiter's moon Europa and Saturn's moon Enceladus both have subsurface oceans that may interact with their host planets' magnetic fields. The solar wind, combined with these magnetic fields, creates environments that could potentially support life, making these moons prime targets for future exploration. The auroras on the gas giants are not just stunning visual displays. They are also windows into the complex interplay between the solar wind and planetary magnetic fields. By studying these phenomena, scientists can learn more about the processes that drive space weather and how they affect planets both within and beyond our solar system. As we continue our journey through the solar system, we'll explore how the solar wind extends its influence even further, shaping the distant Kuiper belt and the icy objects that reside there. Moving further into the outer reaches of our solar system, we now turn our attention to the Kuiper belt, a vast region of icy bodies and dwarf planets that lies beyond Neptune. Here, the solar wind continues to play a subtle yet significant role, shaping the environment of these distant objects in ways that are still being uncovered by scientists. The Kuiper belt is home to countless icy bodies, including Pluto, its most famous resident. While the solar wind weakens as it travels farther from the sun, its influence is still felt even at these great distances. The charged particles of the solar wind interact with the surfaces of these icy objects, slowly altering their composition over time. This process, known as space weathering, can cause changes in the color and texture of the surfaces, making them appear darker or redder as they are bombarded by the solar wind over millions of years. One of the most intriguing aspects of the solar wind's interaction with the Kuiper belt is its role in the formation of comets. Many comets originate in this region, and as they are nudged by gravitational forces into orbits that bring them closer to the sun, the solar wind begins to have a more dramatic effect. The intense heat and radiation from the sun, combined with the solar wind, cause the icy surfaces of these comets to vaporize, creating the spectacular tails that we see from Earth. The solar wind also contributes to the thin atmosphere, or exosphere, that surrounds some of the larger Kuiper belt objects. For example, Pluto has a tenuous atmosphere that is constantly being shaped by the solar wind. As the solar wind interacts with Pluto's atmosphere, it can strip away particles, creating a tail-like structure similar to those seen on comets. This process provides valuable insights into how the solar wind affects even the most distant objects in our solar system. Studying the Kuiper belt and its interaction with the solar wind is no easy task, given its immense distance from Earth. However, missions like New Horizons, which flew past Pluto in 2015, have provided us with unprecedented data about this mysterious region. These observations have revealed that the solar wind's influence extends far beyond the inner solar system, shaping the evolution of objects in the Kuiper belt over billions of years. As we continue to explore the outer edges of our solar system, the Kuiper belt serves as a reminder of the solar wind's far-reaching power. Its ability to shape and transform even the most distant objects highlights the interconnected nature of our solar system, where the sun's influence is felt in every corner, no matter how remote. Next, we'll delve into how the solar wind helps scientists study the boundary between our solar system and the vast expanse of interstellar space, revealing even more about the mysteries of the cosmos. As we venture beyond the Kuiper belt, the solar wind becomes a key player in one of the most fascinating areas of space exploration, the boundary between our solar system and the vast, uncharted realm of interstellar space. This boundary, where the sun's influence begins to wane, is a region of immense scientific interest, and the solar wind provides critical clues about what lies beyond. The solar wind creates a protective bubble around our solar system, known as the Heliosphere. This bubble is formed as the solar wind streams outward, pushing against the particles and magnetic fields of interstellar space. Think of it as a cosmic shield, protecting the planets and other objects within our solar system from the harsh conditions of interstellar space. But as the solar wind travels farther from the sun, it begins to slow down, eventually meeting resistance from the interstellar medium. This point of interaction is called the heliopause, and it marks the edge of the sun's influence. Beyond this boundary, the solar wind can no longer dominate, and the environment is shaped by the particles and magnetic fields of interstellar space. Studying this boundary helps scientists understand not only the limits of our solar system, but also the nature of the space that lies beyond. One of the most groundbreaking missions to explore this boundary is Voyager 1, which became the first human-made object to cross into interstellar space in 2012. As Voyager 1 traveled through the Heliosphere, it sent back data showing a dramatic drop in solar wind particles and an increase in cosmic rays from interstellar space. These observations provided the first direct evidence of the Heliosphere and confirmed that the solar wind plays a crucial role in defining the boundary of our solar system. The solar wind also helps scientists study the properties of the interstellar medium itself. By observing how the solar wind interacts with this region, researchers can learn about the density, temperature, and magnetic fields of the space between stars. This information is vital for understanding the broader structure of our galaxy and how our solar system fits into the cosmic landscape. As we continue to explore this boundary, the solar wind remains an essential tool for unlocking the mysteries of interstellar space. Its interactions with the interstellar medium reveal not only the limits of the sun's influence, but also the dynamic processes that shape the universe beyond our solar system. Next, we'll take a closer look at the Parker Solar Probe, a mission designed to study the solar wind up close and provide groundbreaking insights into its behavior and origins. Now, let's turn our attention to one of the most daring missions ever launched to study the solar wind, the Parker Solar Probe. This remarkable spacecraft is on a mission to get closer to the sun than any human-made object has ever gone, diving into the sun's outer atmosphere, or corona, to uncover the secrets of the solar wind. The Parker Solar Probe was designed to answer some of the most pressing questions about the sun and its influence on the solar system. Why is the sun's corona so much hotter than its surface? How does the solar wind accelerate to such incredible speeds? And what drives the complex dynamics of the sun's magnetic field? To find these answers, the probe is equipped with cutting-edge instruments that can measure the solar wind's particles, magnetic fields, and energy in unprecedented detail. One of the most astonishing aspects of the Parker Solar Probe is its ability to withstand extreme conditions. As it swoops closer to the sun, it faces temperatures of nearly 2 million degrees Fahrenheit. To survive this inferno, the probe is protected by a thick heat shield made of advanced carbon composite materials, which keeps its instruments at a comfortable temperature while allowing it to gather data from the heart of the solar wind. Already, the Parker Solar Probe has made groundbreaking discoveries. It has observed the solar wind accelerating to supersonic speeds, revealing how the sun's magnetic fields play a crucial role in shaping its flow. The probe has also captured detailed images of the corona, showing structures like solar flares and coronal loops in stunning clarity. These observations are helping scientists piece together the puzzle of how the sun generates and releases energy into space. But the mission isn't just about understanding the sun, it's also about protecting our planet. By studying the solar wind up close, the Parker Solar Probe provides critical data that can improve our ability to predict space weather. Solar storms, driven by the solar wind, can disrupt satellites, power grids, and communication systems on Earth. With better insights into how these storms form, we can develop strategies to mitigate their impact and safeguard our technology-dependent world. As the Parker Solar Probe continues its journey, it promises to deliver even more groundbreaking insights into the solar wind and the sun's behavior. Each orbit brings it closer to the sun, offering a front row seat to the dynamic processes that shape our solar system. Next, we'll explore the historical discoveries that have shaped our understanding of the solar wind, tracing the journey from early theories to modern missions like the Parker Solar Probe. Now, let's take a step back in time to uncover how our understanding of the solar wind has evolved over the centuries. The story of the solar wind begins long before modern technology, with early astronomers observing the sun and wondering about its mysterious influence on the cosmos. In the late 19th century, scientists began to suspect that the sun emitted more than just light and heat. British astronomer Richard Carrington made a groundbreaking observation in 1859 when he witnessed a massive solar flare, followed by a geomagnetic storm on Earth. This event hinted at a connection between the sun and Earth's magnetic environment, though the exact mechanism remained a mystery. The idea of the solar wind as we know it today began to take shape in the early 20th century. In the 1950s, physicist Eugene Parker proposed a revolutionary theory that the sun's corona continuously emits a stream of charged particles, which he called the solar wind. At the time, many scientists were skeptical, but Parker's calculations and predictions laid the foundation for modern solar physics. The first direct evidence of the solar wind came in the 1960s, thanks to the Mariner 2 spacecraft. As it traveled toward Venus, Mariner 2 detected a steady flow of charged particles streaming from the sun, confirming Parker's theory. This discovery marked a turning point in our understanding of the sun's influence on the solar system. Over the following decades, missions like the Pioneer and Voyager probes expanded our knowledge of the solar wind's behavior and its interactions with planets and other celestial bodies. These missions revealed the solar wind's varying speeds, its role in shaping planetary magnetospheres, and its ability to strip away the atmospheres of planets like Mars. In more recent years, missions like the Solar and Heliospheric Observatory, or SOHO, and the Parker Solar Probe have taken solar wind research to new heights. These missions have provided unprecedented insights into the sun's magnetic field, the acceleration of the solar wind, and its impact on space weather. The journey from early theories to modern missions has been a testament to human curiosity and ingenuity. Each discovery has brought us closer to understanding the sun's dynamic nature and its profound influence on the solar system. Next, we'll explore how the sun's magnetic field shapes the solar wind, creating the complex and ever-changing flow of particles that defines our cosmic neighborhood. Now, let's turn our attention to the sun's magnetic field, a powerful force that plays a crucial role in shaping the solar wind. The sun isn't just a ball of hot gas, it's a dynamic, magnetic powerhouse. Its magnetic field is generated by the movement of charged particles within its interior, creating a complex web of magnetic lines that extend far into space. These magnetic lines aren't static. They twist, turn, and sometimes even snap, releasing enormous amounts of energy. This activity directly influences the solar wind, guiding its flow and determining its structure. When the sun's magnetic field lines are closed, they trap particles near the sun's surface, creating regions of slower, denser solar wind. But when these lines open up, they allow particles to escape more freely, forming faster streams of solar wind. The sun's magnetic field also gives the solar wind its distinctive patterns. Near the sun's equator, the magnetic field is relatively stable, producing a steady, slow solar wind. But closer to the poles, the magnetic field is more open, allowing particles to accelerate and create faster streams. This interplay between open and closed magnetic regions creates the solar wind's complex, ever-changing flow. One of the most fascinating aspects of the sun's magnetic field is its ability to shape the solar wind into structures like coronal loops and magnetic arcs. These features are visible during solar eclipses or through specialized telescopes, revealing the sun's magnetic influence in stunning detail. As the solar wind travels outward, it carries the sun's magnetic field with it, creating a vast magnetic environment that extends throughout the solar system. This magnetic field interacts with planets, moons, and other celestial bodies, influencing their magnetic environments and even shaping their atmospheres. Understanding the sun's magnetic field is key to unraveling the mysteries of the solar wind. It's a reminder that the sun isn't just a source of light and heat. It's a dynamic, magnetic force that shapes the very fabric of our solar system. Next, we'll explore how the solar wind affects the flow of cosmic rays into the solar system, revealing yet another layer of its cosmic influence. Now, let's shift our focus to another fascinating aspect of the solar wind: its role in modulating cosmic rays. Cosmic rays are high-energy particles that travel through space at nearly the speed of light, originating from distant supernovae, black holes, and other powerful cosmic events. But as these particles approach our solar system, they encounter the solar wind, which acts as a kind of cosmic shield, influencing their journey in surprising ways. The solar wind, with its magnetic field carried from the sun, creates a protective bubble around our solar system, known as the Heliosphere. This bubble isn't just a passive barrier, it's a dynamic region where the solar wind interacts with incoming cosmic rays. As these high-energy particles enter the Heliosphere, they collide with the magnetic fields embedded in the solar wind, causing them to scatter and lose energy. This process, known as cosmic ray modulation, effectively reduces the intensity of cosmic rays reaching the inner solar system. Interestingly, the strength of this modulation isn't constant. It fluctuates with the sun's activity cycle. During periods of high solar activity, when the sun's magnetic field is stronger and the solar wind is more intense, cosmic rays are deflected more effectively. This means fewer cosmic rays penetrate deep into the solar system. Conversely, during periods of low solar activity, the solar wind weakens, allowing more cosmic rays to reach planets like Earth. This modulation has significant implications for space exploration and even life on Earth. Cosmic rays can pose risks to astronauts and spacecraft, damaging electronics and increasing radiation exposure. By understanding how the solar wind modulates these particles, scientists can better predict and mitigate these risks. Additionally, cosmic rays play a role in Earth's atmosphere, contributing to cloud formation and potentially influencing climate patterns. The solar wind's ability to modulate cosmic rays is a testament to its far-reaching influence. It's not just a stream of charged particles. It's a dynamic force that shapes the environment of our solar system, protecting us from the harshest elements of the cosmos. Next, we'll explore how the solar wind connects to solar eruptions, like coronal mass ejections, and the dramatic effects these events can have on space weather. Now, let's turn our attention to one of the most dramatic events in the solar system, solar eruptions, and how they intertwine with the solar wind. Among these eruptions, coronal mass ejections, or CME, stand out as colossal bursts of solar material and magnetic fields hurled into space. These events are not just spectacular to observe, they are deeply connected to the behavior of the solar wind, creating a dynamic interplay that shapes space weather. When a coronal mass ejection occurs, the sun ejects billions of tons of charged particles and magnetic fields into space at incredible speeds, often exceeding millions of miles per hour. These eruptions are driven by the sun's magnetic activity, particularly when twisted magnetic fields suddenly snap and release their stored energy. As the CME travels outward, it merges with the solar wind, amplifying its intensity and creating a shock wave that ripples through the heliosphere. This interaction between CMEs and the solar wind can have profound effects. The combined force of the solar wind and the CME can accelerate particles to even higher energies, creating what scientists call solar energetic particles. These particles can pose significant risks to satellites, spacecraft, and even astronauts, as they can penetrate shielding and disrupt electronics. On Earth, the impact of these events can be felt through geomagnetic storms, which can interfere with power grids, communication systems, and even GPS signals. One of the most fascinating aspects of this connection is how CMEs can alter the structure of the solar wind. As a CME propagates through space, it compresses the solar wind ahead of it, creating a dense, high-speed stream. Behind the CME, the solar wind may become turbulent, with magnetic fields tangled and chaotic. This turbulence can persist for days, influencing the flow of particles and energy throughout the solar system. The relationship between the solar wind and CMEs also provides valuable insights into the sun's behavior. By studying how these eruptions interact with the solar wind, scientists can better predict the timing and intensity of space weather events. This knowledge is crucial for protecting our technology-dependent society and ensuring the safety of future space missions. As we continue to explore the mysteries of the solar wind, the connection to solar eruptions like CMEs reminds us of the sun's immense power and its ability to shape the environment of our solar system. Next, we'll delve into how the solar wind influences human space exploration and the challenges it presents for astronauts venturing beyond Earth's protective magnetosphere. As we venture further into the cosmos, the solar wind becomes more than just a fascinating phenomenon. It's a critical factor in the safety and success of human space exploration. For astronauts traveling beyond Earth's protective magnetosphere, the solar wind presents both challenges and opportunities that must be carefully navigated. One of the most immediate challenges is the constant bombardment of charged particles. Without Earth's magnetic field to shield them, astronauts are exposed to higher levels of radiation from the solar wind. This radiation can damage cells, increase the risk of cancer, and even affect the central nervous system over time. To mitigate these risks, spacecraft are equipped with shielding materials, and missions are carefully timed to avoid periods of heightened solar activity, such as solar storms or coronal mass ejections. But the solar wind isn't just a hazard, it also offers unique opportunities for exploration. For instance, the solar wind's interaction with planetary surfaces can reveal valuable information about the composition of other worlds. On the Moon, for example, the solar wind has implanted charged particles into the lunar soil, creating a resource that could potentially be harvested for oxygen or fuel in future missions. This concept, known as in situ resource utilization, could revolutionize how we approach long-term space travel. Another intriguing possibility lies in harnessing the solar wind itself. Scientists are exploring the idea of using magnetic sails, or mag sails, to propel spacecraft. These sails would capture the momentum of the solar wind, allowing spacecraft to travel vast distances without the need for traditional fuel. While still in the experimental stage, this technology could open up new frontiers for human exploration, making distant destinations like Mars or even the outer planets more accessible. Of course, the solar wind also plays a role in shaping the environments astronauts will encounter. On Mars, for example, the planet's thin atmosphere offers little protection from the solar wind, which has contributed to the loss of much of its original atmosphere over billions of years. Understanding these processes is crucial for planning future missions, as it helps scientists predict the conditions astronauts will face and develop strategies to protect both humans and equipment. As we look to the stars, the solar wind reminds us that space is not a void, but a dynamic, ever-changing environment. By studying its effects and learning to adapt, we can turn its challenges into opportunities, paving the way for humanity's next great adventure. Next, we'll explore how the solar wind could even play a role in the search for extraterrestrial life, and what it might tell us about habitable worlds beyond our solar system. As we turn our gaze beyond our solar system, the solar wind takes on a new significance, one that could hold the key to finding life among the stars. The search for extraterrestrial life often begins with the hunt for habitable zones, regions around stars where conditions might be just right for liquid water to exist. But what role does the solar wind play in shaping these zones? The solar wind, with its constant stream of charged particles, can have a profound impact on the atmospheres of distant planets. For a planet to support life as we know it, it needs a stable atmosphere that can retain heat and protect against harmful radiation. However, if a planet orbits too close to its star, the intense solar wind could strip away its atmosphere over time, leaving it barren and lifeless. On the other hand, planets with strong magnetic fields, like Earth, can deflect the solar wind and preserve their atmospheres, creating a protective shield that fosters life. This interaction between the solar wind and planetary atmospheres helps scientists identify which planets might be worth a closer look. For example, when studying exoplanets, planets orbiting other stars. Astronomers pay close attention to the strength of the star's solar wind and the planet's magnetic field. A planet with a weak magnetic field in a star system with a strong solar wind is less likely to retain its atmosphere, making it a poor candidate for habitability. But the solar wind's influence doesn't stop there. It also plays a role in shaping the space environment around stars, which can affect the stability of planetary systems. In some cases, the solar wind can even help clear away debris, creating a cleaner orbital path for planets. This process, known as stellar wind clearing, can contribute to the formation of stable, long-lasting planetary systems where life might have a chance to thrive. Understanding the solar wind's behavior around other stars is also crucial for interpreting the signals we receive from distant worlds. For instance, when astronomers detect signs of water vapor or other potential biomarkers in a planet's atmosphere, they must consider whether the solar wind could have altered or erased those signals over time. By studying the solar wind in our own solar system, we gain valuable insights into how it might behave elsewhere, helping us refine our search for habitable worlds. As we continue to explore the cosmos, the solar wind serves as both a guide and a reminder. It reminds us that the conditions for life are delicate, shaped by the interplay of forces we are only beginning to understand. And it guides us toward the stars that might host planets where life could flourish, offering a glimpse into the vast possibilities that lie beyond our solar system. Next, we'll delve into how the solar wind has shaped the evolution of our own solar system over billions of years, and what it tells us about the forces that have shaped the universe itself. Now, let's take a step back in time to explore how the solar wind has played a pivotal role in shaping the very fabric of our solar system over billions of years. From its earliest moments to the present day, this relentless stream of charged particles has been a driving force behind the evolution of planets, moons, and even the smallest grains of cosmic dust. When the solar system first formed, it was a chaotic, swirling cloud of gas and dust. As the sun ignited and began to shine, its intense heat and radiation pushed lighter materials outward, while its magnetic field began to channel charged particles into the solar wind. This wind, flowing outward in all directions, acted like a cosmic broom, sweeping away loose debris and helping to clear the early solar system. Over time, this process allowed planets to form and settle into stable orbits, free from the constant bombardment of leftover material. But the solar wind's influence didn't stop there. As planets began to take shape, the solar wind continued to shape their surfaces and atmospheres. For example, on smaller, rocky worlds like Mercury and the Moon, the solar wind bombarded their surfaces, breaking down rocks and creating fine layers of dust. Over billions of years, this constant erosion has left these worlds with barren, cratered landscapes, a testament to the solar wind's relentless power. For planets with atmospheres, the solar wind has been both a creator and a destroyer. On Earth, the solar wind interacts with our magnetic field, creating the magnetosphere that protects us from harmful radiation. This shield has allowed life to flourish, making Earth a rare oasis in the cosmos. But on planets like Mars, which lacks a strong magnetic field, the solar wind has slowly stripped away its atmosphere over time, leaving it cold and desolate. Even the outer planets, with their massive magnetic fields, have been shaped by the solar wind. Jupiter and Saturn, for instance, experience intense interactions with the solar wind, creating stunning auroras and influencing the behavior of their moons. These interactions have helped shape the complex systems of rings and moons that we see today, showcasing the solar wind's far-reaching influence. The solar wind has also played a role in the distribution of water and other volatile materials throughout the solar system. As comets and icy bodies travel through the solar system, the solar wind can erode their surfaces, releasing water vapor and other compounds into space. This process has contributed to the presence of water on planets like Earth, and even on moons like Europa and Enceladus, where subsurface oceans hint at the possibility of life. As we look back over the solar system's history, it's clear that the solar wind has been a constant shaping force. From clearing the early solar system to sculpting the surfaces of planets and moons, its influence is written across the cosmos. And as we continue to explore, we'll uncover even more about how this invisible stream of particles has shaped the story of our solar system, and perhaps the story of life itself. Next, we'll turn our attention to the future, exploring how upcoming missions aim to unlock even more secrets of the solar wind and its role in the universe. As we look ahead, the mysteries of the solar wind continue to beckon scientists and explorers alike. The next chapter in our understanding of this cosmic phenomenon lies in the hands of groundbreaking missions designed to study the solar wind up close. These missions promise to unlock secrets that have remained hidden for billions of years, offering us a deeper glimpse into the forces that shape our solar system. One of the most exciting missions on the horizon is the Parker Solar Probe, which has already begun its daring journey into the Sun's corona. This spacecraft is designed to fly closer to the Sun than any mission before it, enduring extreme heat and radiation to gather unprecedented data about the solar wind. By measuring the speed, density, and magnetic fields of the solar wind at source, the Parker Solar Probe is helping scientists understand how the solar wind is accelerated and how it evolves as it travels through space. Each orbit brings new insights, revealing the intricate dance between the Sun's magnetic field and the charged particles it propels into the cosmos. Another mission, poised to revolutionize our understanding, is the European Space Agency's Solar Orbiter. Unlike the Parker Solar Probe, which focuses on the Sun's immediate environment, the Solar Orbiter is designed to study the Sun from a slightly greater distance, capturing high-resolution images of the solar surface and its atmosphere. This mission aims to uncover how the Sun's magnetic field generates the solar wind and how it influences the broader Heliosphere. By combining its observations with data from the Parker Solar Probe, scientists hope to piece together a comprehensive picture of the solar wind's origins and behavior. Looking further into the future, NASA's Interstellar probe mission is set to explore the very edge of the solar system, where the solar wind meets the interstellar medium. This mission will travel beyond the heliopause, the boundary where the Sun's influence wanes, and into the uncharted territory of interstellar space. By studying the interaction between the solar wind and the interstellar medium, the interstellar probe will provide critical insights into how our solar system interacts with the galaxy at large. This mission could answer fundamental questions about the nature of the Heliosphere and its role in shielding the solar system from cosmic rays. These missions, along with others in development, represent a new era of solar and heliospheric exploration. They are not just about gathering data, they are about rewriting our understanding of the sun, the solar wind, and their profound impact on the cosmos. As these missions unfold, they will undoubtedly reveal new mysteries, challenging us to think differently about the universe and our place within it. With each discovery, we move closer to unraveling the secrets of the solar wind, a force that has shaped our solar system since its birth. And as we prepare to explore even further, we are reminded that the story of the solar wind is far from over. It is a story that continues to unfold, one mission at a time. Next, we'll explore how the solar wind connects to the sun's life cycle, shedding light on how this dynamic force evolves as our star ages. As we turn our gaze to the sun's life cycle, we uncover a fascinating connection between the solar wind and the evolution of our star. Just as the sun itself changes over billions of years, so too does the solar wind, reflecting the dynamic nature of our closest star. This relationship offers a window into the sun's past, present, and future, revealing how the solar wind has shaped, and will continue to shape, the solar system. In its early stages, the sun was a young, energetic star, and its solar wind was likely far more intense than it is today. During this period, the sun's magnetic activity was at its peak, generating powerful bursts of charged particles that streamed outward into space. These early solar winds played a crucial role in clearing away the remaining gas and dust from the solar system's formation, helping to shape the planets and other celestial bodies we see today. Over time, as the sun matured, its magnetic activity began to stabilize, and the solar wind became more consistent, though still capable of dramatic fluctuations. As the sun continues to age, its solar wind will undergo further changes. In the distant future, when the sun enters its red giant phase, its outer layers will expand, and its magnetic field will weaken. This will cause the solar wind to become less dense but more erratic, as the sun's surface becomes more turbulent. During this phase, the solar wind will carry away a significant portion of the sun's mass, gradually thinning its outer layers and altering its gravitational influence on the solar system. This process will have profound effects on the planets, potentially stripping away atmospheres and reshaping orbits. Even further into the future, as the sun transitions into a white dwarf, its solar wind will diminish dramatically. The once powerful stream of charged particles will fade, leaving behind a faint, steady flow. At this stage, the sun's influence on the solar system will wane, and the solar wind will no longer play the dominant role it once did. Yet, even in this quiet phase, the remnants of the solar wind will continue to interact with the interstellar medium, leaving a lasting imprint on the cosmos. Understanding the solar wind's connection to the sun's life cycle not only deepens our knowledge of our own star, but also provides insights into the behavior of other stars throughout the universe. By studying how the solar wind evolves, scientists can better predict the future of our solar system and uncover clues about the life cycles of stars in distant galaxies. This ongoing exploration reminds us that the sun, like all stars, is a dynamic and ever-changing force, and its solar wind is a testament to the intricate interplay between a star and its surroundings. As we reflect on the sun's journey through time, we are reminded that the story of the solar wind is deeply intertwined with the story of the sun itself. Next, we'll bring our exploration to a close by summarizing the key points we've uncovered about the solar wind and its profound impact on the cosmos. As we bring our journey through the mysteries of the solar wind to a close, let's take a moment to reflect on what we've uncovered. The solar wind, a stream of charged particles flowing from the sun, is far more than just a cosmic breeze. It is a powerful force that shapes the very fabric of our solar system, influencing everything from the planets to the distant reaches of interstellar space. From its birth in the sun's corona to its journey across billions of miles, the solar wind carries with it the story of our star's life and the dynamic processes that define it. We've seen how the solar wind interacts with Earth's magnetosphere, creating stunning auroras and protecting us from harmful cosmic radiation. We've explored its role in shaping comets, stripping away planetary atmospheres, and even influencing the evolution of the solar system over billions of years. Through missions like the Parker Solar Probe, we've gained unprecedented insights into this enigmatic phenomenon, revealing its complexities and its profound impact on space weather and human exploration. But the story of the solar wind doesn't end here. As the sun continues to evolve, so too will the solar wind, reminding us that our solar system is a living, breathing entity, constantly changing and adapting. This ever-shifting dance between the sun and its solar wind offers us a glimpse into the broader workings of the universe, connecting us to the countless stars and galaxies beyond our own. As we look to the stars, let's carry with us a sense of wonder and curiosity. The solar wind is just one of the many cosmic mysteries waiting to be unraveled, a reminder of how much we have yet to discover. So, the next time you gaze at the night sky, remember the invisible stream of particles flowing from the sun, shaping the cosmos in ways we are only beginning to understand. Thank you for joining us on this journey through the mysteries of the solar wind. If you enjoyed this exploration, don't forget to like, subscribe, and hit the notification bell for more cosmic adventures. Until next time, keep looking up and wondering about the infinite mysteries of the universe. you.